right, recording is rolling. So it's Wednesday, April 5th. Doing a lab today, resistivity of dough. So Play-Doh actually has a conductivity, and then the reciprocal of that is resistivity, right? Like a resistor. Right? So this will actually transmit electricity. But I wonder how much, like how conductive is it? Or you guys are gonna go with the reciprocal question, like how much resistance, right? And then each material will have some associated resistivity. Like one of the things wonder with you guys was suppose you have like a wire, and I'll have you guys make a cylinder out of dough. But if you zoom in on a wire, it could be like a cylinder shape, right? Or make this into a cylinder, right? And this could have some length, call that L. It has some cross-sectional area, call that A for area. Okay. One of the measurements you guys are going to do today is measure the diameter, so I'll call that D. Right. So, and then how much resistivity, or how much resistance from end to end? Right. Well, the longer the wire, the more the resistance. The fatter the wire, the less resistance. Right. Easier to push electricity through a fatter wire. Right? But one more thing is this resistivity, and we're going to use a Greek letter rho for that. In the past, we've used it for density, but today it represents resistivity. So resistivity. So like copper versus aluminum, if you have two wires that were otherwise identical, like same length, same size, blah, 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 but one was copper and one was aluminum, I bet those would transmit electricity differently, right? Because they have different resistivity. So I wonder what it is for this material. Well, so we're gonna find out. But the relationship here for these variables is that the resistance from end to end, so if you go from like this end to this end, like what's the resistance in ohms? Resistance in ohms is equal to, well, the longer it is, the more the resistance. That's a direct relationship. The more cross-sectional area, the less resistance. That's a inverse relationship. Okay. And then resistivity, you put right here. So rho L over A, right? You guys remember that? Familiar? All right. I want to wire this up and show you guys this does work. So I've got my cell phone leads here. I've got here, show you guys this does. Right, there's some voltage going across there. Boom. There we go. Right. So light up the light. So get there. Right. How about this Joe cylinder? Make sure my LED works too. Which way does this go? That way. Okay. So what if I plug one lead and say like right there, okay, and put this here, like I'm going to bridge this out to this other lead. Okay. Now there's only a short distance here, so let me try the full length. Let me see if the full length works. Okay. So hook this lead here. Does this turn on? Oh, actually it does. It does. Okay. So there's an electric current going through the entire Go cylinder, and then it's bridging through this LED and then out to here. Okay. So there's a voltage drop across the cylinder. I don't know exactly how much, but I can break out the this multimeter and start making some measurements. Okay. So you guys see that? Yeah. Okay. So there has to be a current flowing through that. You guys see that? All right. So put this aside, and let's look at this. Okay. Oh, yeah. Thank you. We get you these pages. Yeah. All right. So we've got this big old table, and last step is going to lead to resistivity, right? So I will demo this whole thing for you guys, and then you'll see, right? There's a diagram down here to remind you guys how to connect the ammeter and how to connect the voltmeter, right? So series versus parallel, but you guys remember that from the other day. So say I try this. So here's my Doe cylinder, like this right here. Let's do this. Right, what's the diameter of this in meters? In meters. Okay? So you guys know 1 meter is about 3 floor tiles long. That's a really big distance. So this would be a tiny decimal of a meter, won't it? Right, same getting here. I'm looking at, I'll call it 2 centimeters. Let's call it. Now, if that's 2 centimeters, 2 centimeters, 0.02, right? Right. So is that 0.02 meters, correct? Right? Because see, last class I had some students writing like 0.2 meters. No. 0.2 meters would be like most of the ruler. It'd be like if you had a Doe cylinder that was like this big. Whoa, right? That right? 0.02 meters, that's 2 centimeters, right? Right. What's the cross-sectional area in square meters? Right, now here's where, let's look at the geometry of a circle. So at a circle. Right. Yeah, the area of a circle is pi r squared. Yeah. now, since the page has diameter on it, we'll just play off that. Thank you. Guys, here. This is here. This is here. All right. Present. All right. So, can you guys get the area of a circle in terms of its diameter? How about this? What is diameter compared to radius? That'd be diameter is equal to 2 times the radius, right? Okay. So if I see radius, do you think I can go diameter divided by 2 is equal to the radius? Right, substitute that right there. So the area of a circle is pi times diameter over 2 quantity squared. Diameter gets squared. The 2 also gets squared. You bring that on up front. 2 squared is 4. So we go the area of a circle is pi on 4 times diameter squared. Okay. So this is going to be important in time. This is about to be important right here. Right. You guys might want to jot that down on this half page. Okay. Area is pi on 4 times diameter squared. Okay. That's a good one to know. Right. Okay. There's that. Remember taking engineering classes back in the day, we use that quite a bit for cross-sectional areas of pipes, because a lot of pipes are sorted by their diameters. Oh, yeah. Okay, give you the page. Oh, okay, you got one? Right. Okay. Length in meters. Okay, so, okay, try this. This is 5.5 centimeters long. So 5.5 centimeters. Oops, back up. Well, okay, let's see. So is that 0.55 meters? 0.055 meters, right? 0.055 meters would be 5.5 centimeters. Okay, since I'm doing this whole thing with you guys, let's calculate what's pi over 4 times diameter squared. So pi over 4, right? Put that in parentheses, times diameter of 0.02 meters, and then square that. And that is, it should be a tiny, tiny number, which makes sense, right? So in my case, 0.0003, 0.0003. Actually, it just follows the digits of pi after that, 314,159. Of course, it's going to be a tiny number because 1 square meter, that's like approximately 9 floor tiles. Right? Not exactly, but pretty close. So you're talking about the cross-sectional area of this thing, tiny, tiny, right? Makes sense? All right. Voltage. Okay, now we've got to break out this voltmeter. Okay? You guys remember measuring volts, voltage in volts or current in amps? You need to do some different processes. So these are plugged in the correct way. So the black one just even COM, the red one, once it says volts, it switches over to DC volts, get the decimal place in a good spot. Okay? And then let's wire this up. Right? Now, you don't actually need an LED for this. I was just doing that to demonstrate. I did leave some LEDs back there. So if you want to try that, I think I did like create a bridge and see. I'll do. Can. Okay. But that should be transmitting electric current right there. Try not to smash that too much because I don't want to change my length. But it should be transmitting some current. Right? If you do the full length, then that length would also apply. If you want to do like half of that, then you would only put in half your length right here. Like if I went from here to here, I might have to do that. I'm going to see if this still works. Let's see. What's the voltage from here to here? Right. Well, I'd like to connect it directly to my leads. There we go. Oops, I got negative because I got my leads backwards, but it said negative 4.8. Let's see if I get a positive 4.8. Positive 4.8. You guys see that? 4.8? Right. So let's go to voltage. I'm going to do 4.8 volts. And this is a cell phone charger that's about 5 volts. That looks right. Okay. Yeah, plus or minus a little bit. What is the current in amps? Okay, now current in amps, I got to make a few switches. So I'm going to pull this out, switch it over here, current in amps. Okay. All right, switch this toggle to right here. Right? Okay, all good. Okay. And then now the other thing I have to do, remember, exactly as it shows in the setup, is break open my circuit and force the current to flow through the multimeter, Ooh, it's small, but it's just registering. About 0.1. whoops, if I flip my leads, see if that's, all right, let's call it 0.1 amps. You guys see 0.1? Okay. So it barely registers. Let's call it 0.1 amps, right? Tip, if you make this cylinder longer, the resistance would go up. So that would decrease your current more and more. So this is probably as long a cylinder as you can use. If you use a smaller cylinder, it might give you a slightly better reading. Okay, you guys good? So flip that off, this aside. All right. What's the resistance in ohms? All right, let's do a little math here. You guys remember Ohm's law? I usually use this version of it. The current that flows is the voltage acting on the resistance. Some textbooks just go for this version of it, V equals IR. I mean, they're the same thing. But we're interested in what is the resistance. So would that have to be V divided by I? Is that what that would be? V over I, right? Oh, here's your volts. Here's your amps. Right? So 4.8 divided by 0.1, could that be like 48 ohms, right? So from end to end, that's about 48 ohms of resistance. It's kind of like a 48 ohm resistor. Let's get that. Okay, and finally, let's combine this resistance with this geometry that we got at the beginning to figure out what is the resistivity of this dome. Okay? So now we're back to this right here. Okay. Well, I need to rearrange this guy. So if we're solving for this resistivity, can I take the cross-sectional area, multiply it up, and take the length and divide it down? So should that give me resistivity is equal to resistance times cross-sectional area divided by the length? Okay, is that what that would be? All right. All right. Guys good? All right, so let's put that together. So the resistance is 48 ohms. The cross-sectional area was this 0.0003 and 1415 if you want. And then divided by the length of 0.055 meters. Okay? If they're all base SI units, some of these numbers are really tiny. That's okay. And let's see what we get. 0.26 ohm meters. Ohm meter is the unit for resistivity, which if you follow the units, that's exactly what it would be. Okay? I Googled this ahead of time, and I said, what is the resistivity of Play-Doh? Whoa, all right, I'm gonna share my screen on this one. All right, let me flip the screen over here. Show you guys this. Okay. Now, it does depend on the color of Play-Doh. Right? Different colors have a little bit different resistivity. Just for the video, let's share screen 2. There you go. What is the resistivity of Play-Doh? 0.24 ohms. Look at that. Ohm meters. Ohm meters, because it's resistivity as a material, right? 0.24 ohm. 0.24 ohm meters. All right. Which is exactly, well, right in line with what we got. It's extremely close. Okay. You guys good so far? Okay. You'll probably have time to try a few of these. So try mixing it up a little bit. Like, what if you try different shaped cylinders? You can make them longer, shorter. You could make them fatter, skinnier. Play around with that and see how that works. And try this too. Here, flip your page over. Okay. Couple of axes. Okay. Now, since resistance is equal to resistivity times length over area, right? Been using that. That's okay. That's that right there, right? Just copy paste that. If you put resistance in ohms on the vertical axis and length over area on the horizontal axis and say, what would this be? Meters divided by square meters. That's like 1 over meters, which is a weird unit. Think about it. An abstract idea. But so right? If you make different shaped cylinders that have like different ratios of length to cross-sectional area, I bet all these points should line up pretty well in a straight line. If you can do, you should have time for 3 at least. Try this out. Do 3, graph them, and see if they do line up in a straight line. Because if they do, what would the slope represent? Resistivity. Boom, right there. Right. Right. So you guys okay? You guys good? Right. So yeah, so you guys got all the materials back there. Just make different cylinders. Grab these numbers, and then should have about 5-10 minutes at the end of class, and then make a graph and see if they actually do line up like that. All right, and then throw that in the gray tray.